A very warm good morning to all. I am Professor Bharti from the Department of Aerospace Engineering, Alliance University. Like to welcome all of you for the third ATAL Faculty Development Program on Advancements in CFD using Fluidine. We are privileged to have our first speaker today, Dr. Anil Kumar, Director, Multiphysics Fluidine India Private Limited. Dr. Anil received doctorate in aerospace engineering with specialization in solid propellant combustion from IISc Bangalore in the year 2001. Dr. Anil is a postdoc fellow in the Department of Fuel and Energy at University of Leeds, UK. Dr. Anil Kumar is working with Fluidine from last 19 years and currently he is working as Director, Multiphysics Division, Fluidine India Private Limited. Dr. Anil Kumar handled several projects related to nuclear, defense, electromagnetic, and electrochemistry. His area of expertise includes CFD, heat transfer, turbulent combustion modeling, multiphysics flows, radioactivity, electromagnetics, and fluid structure interaction. Now, I would like to take the privilege to invite Dr. Anil Kumar, Director, Multiphysics Fluidine India Private Limited, to present on the topic multi-phase flows. Over to you, sir.
Thank you, madam, for the introduction. And good morning and namaste to all the participants. Shall I share my screen and
Yes, sir. Please.
start? Okay. Okay. Today's topic is multi-phase flows. First, we will look at some examples of multi-phase flows and try to identify the basic characteristics. And then based on these characteristics and the physical processes involved, we will look at the equations, mathematical equations required to simulate these flows. Then we will have a brief discussions on various methods using some of the studies we had done in the last 5 to 10 years. Then we can have a discussion. Am I audible and visible?
Yes, sir.
Yes, sir.
Okay, thank you. Multi-phase flows involves the flow of immiscible phases. As we know, there are 3 phases, or 4 rather, like 4 states of the matter, like solid, liquid, gas, and there is something called a supercritical state where there is no clear distinction or interface between the material. So if you look at the different types of flows, one way of classifying them in terms of combination of the phases. So what you see, the picture that you are seeing here on the right hand side, this is a liquid jet in the droplets, liquid jets and droplets in gas stream. All of you might be familiar with our space program, and the term cryogenic liquid rocket engine is very much in news nowadays, partly due to the successful launches of GSLV. If you look at the flow inside such a rocket engine, there is It's like a cylindrical vessel, and at one end there are two injectors, and through the center injector, a stream of liquid oxygen at 90 Kelvin approximately, at very high pressure comes in. While coming in, it is still at the liquid state. And then in the annular section, through an annular opening, the gaseous hydrogen at around 140 or 150 Kelvin comes in, still at very low temperatures. And that hydrogen, when it enters the chamber, is in gaseous state. So you can see that in this flow field, there is a liquid, there is liquid oxygen jet, initially a continuous jet. Then there is gaseous hydrogen. The gaseous hydrogen has a very high velocities compared to that of liquid jet. So there is a shear, and this shear now breaks up the liquid jet to form the droplets and so on. So another type of flow is where both the phases are liquid. You know the examples of oil and water. They are immersible. So if you want to study a flow involving this, it is separating fluid, separate liquids, it can be treated as a multi-phase flow. So one example is shown on the left-hand side. Again, this is related to space launch vehicles. Many times at the launch pad, when the rocket stands, this rocket contains the fuel tanks. For example, if many countries use, for example, Japan, they are doing experiments on rockets using liquefied natural gas, LNG, basically methane, and the LOX as the oxidizer. So in this case, there will be tanks, and in case of any failure or any failure or accident, if these tanks fail, then the liquid in them will spill to the neighboring ground, and both the fuel LNG and the LOX are at very low temperatures, and the ambient temperature is very high, much higher than their boiling points. So as they spill, they will spread over the ground and then evaporate and form a reactive mixture which can explode. So normally risk analysis, consequence analysis are done from safety point of view. So if you want to conduct these studies, you can see that there is a green color. What is shown in green color, it is the LOX, that is liquid oxygen, and what is shown in the red color is liquefied nitrogen gas, and in the blue it is a surrounding air. So it is actually a three-phase flow, two liquids and one gaseous phase. Then there are other combinations. For example, solid particles in liquids, that is liquid and solid. For example, sedimentation of sand particles in rivers, it's an example of solid and liquid flow. Or in solid propellant manufacturing, the propellant grain is made by mixing ammonium perchlorate particles, which are solid, in liquid called hydroxy terminated polybutadiene, which is a highly thick liquid. It's a non-Newtonian slurry. So it is a flow involving liquid and solid. Then there are gas and solid flows. The best example is dispersion of dust particles in air, which we are all familiar with. We are all familiar with dust particles and its flow in the air from the point of air pollution. And this picture here shows one of the studies we have done, which we will see later in detail. But this involved the modeling of an industrial particle filter. It's called backhouse air filter. Here what happens is the air laden with particles, they come in the filter, and these particles gets collected in the filter, and the air goes out. And in the process, the particles change the characteristics of the filter. all of us are familiar with filters because all of us are using N95 mask. We are using masks, these filters. So we will see this in detail later. How to model a filter and the position of particles on the filter and so on. The last category of combination of phases is gas bubbles in liquid. So one example shown here is from the electrochemistry. There is a cell, there is a system called Heroult cell, which is used in the production of aluminum. Oh, the thing is that there is an anode and which is immersed in the liquid metal. When the electricity is applied at the anode, the hydrogen bubbles are formed due to electrochemical reactions. And these bubbles is released, and due to buoyancy, hydrogen is a lighter, hydrogen bubbles are lighter than the liquid. So they, due to buoyancy, they rise in the liquid, and in the process, they generate a flow inside the liquid also. Then there are other examples of liquid and gas, like formation in the atmosphere, water droplets formed in steam turbines due to condensation, and so on. In addition to that, there is a large class of problems involving free surface flows, like ocean waves, or as you can see here, this is a simulation of a drainage system, which again we will see later. So in case of a leak from a tap or some hazardous liquid, they spread on the surface, and the second picture animation shows its flow into the drain. So these kind of studies are done to see whether the drain is completely the system is the pipes, etc., are capable of carrying the liquid. We will see this problem in detail later. So if you keep in mind all these the examples that we have seen, in general, multi-phase flows involve immiscible flow of liquids, gases, and solids. In addition to this, there could be they can get into supercritical state also. So these involve some physical processes which there could be mass transfer between the phases. For example, evaporation of droplets or pyrolysis or burning of solid particles. I think my colleague Chendil had introduced calcination. This was yesterday. So that involves pyrolysis of cold particles or chemical reactions involving solid particles, or condensation of bubbles, which involves phase mass transfer from the gaseous phase into the liquid phase, and so on. Then there could be momentum transfer between the phases, like when a solid particle or liquid particle moving through a gaseous phase, and if there is a difference between the velocities of the phases, there could be momentum exchange. Then the heat transfer between the phases, and also the interfaces between the interface between the phases may change shape, and it is affected by various factors like advection or surface tension, molar pressure, etc. And the phase separation may happen due to various other external forces. In addition to that, there could be other matters like dispersion, turbulent dispersion, or Brownian motion, and so on, collisions between the particles, and so on. I would like to, at this stage, I would like to ask something. How do we go about this presentation? Do I take questions in between the presentation itself or at the end?
So at the end, you can take the questions, sir.
Okay, thank you. So, if you look at the physical characteristics of the multi-phase flows, it introduces a lot of they introduce a lot of challenges to simulate them. You can see that many times there's large difference in densities between the phases. There could be large source terms due to interface mass, momentum, and energy transfer. And the interfaces can be very complex in shapes. And the same problem, there could be multiple flow regimes. Like if you remember the example of the cryogenic engine, initially the liquid jet is a continuum. It's a continuous jet, and later it becomes droplets. And the fluid flow, in the case of multi-phase flow, the fluid, one of the phases can change the characteristics, the geometry. For example, as in the case of the filter, the particles, so first phase is air and the second phase is particle, and the particles can get deposited in the filter, and it will reduce the efficiency of the airflow through the filter. In general, the multi-phase flows have wide range of length and time scales, because different processes may take place at it may require different times. We will see some of the examples with this kind of features. I see that my internet connection is a bit weak, so I will stop my video. So based on this physical process, sorry, 1 second. We can formulate these equations, mathematical equations, to represent these flows. These basically involve conservation of mass, momentum, energy, and phase components for each of the phases, in addition to the net equations of state for each of the phases, and also models for interchange of mass, momentum, and energy between the phases. If you look at the equations, these are the basic equations of multi-phase flows. You can find I have given a list of references, and you can find the details of these equations in various references, especially in the paper by Darvish et al. And Sorrell and others. They give a very good description of all the equations and how these are derived and how various approximations can be made. So my objective here of showing this equation is only to highlight the differences between the equations for multi-phase flows and the single-phase flow. If you look at the, I'll explain it using the first equation, that is a continuity equation, mass conservation equation. If you look at it, the equation for single phase flow involves only partial d rho by dt plus del dot rho I v rho v equal to 0. That is a normal continuity equation. But in the case of mass conservation equation for a phase, for example, for ith phase in this case, in a multi-phase flow, the volume fraction of the phase also is included, because volume fraction means in a control volume or in a small volume, that control volume may contain multiple phases. So the volume fraction of a phase I is the volume of that particular phase divided by the total volume. So that this is one difference. Second difference is that there is a source term. The source term on the right hand side, this is to model the mass transfer between the phases. For example, when there is evaporation of a liquid, then the liquid phase loses some mass, and that mass, the same amount of mass, enters the gaseous phase. So there is a source term for the gaseous phase, and there is a corresponding sink term for the liquid phase. So similarly, for the of you are familiar with Navier-Stokes equation for the momentum conservation based on the Newton's second law. So that equation is also suitably modified using these two terms in general. All the terms are modified by including a volume fraction and also an interface, a source term for interface, source or sink term for interface exchange. This takes care of this source term takes care of the drag or any other type of momentum exchange. Then the energy conservation equation also has a source term to take care of evaporation, the latent heat of evaporation, or the heat of pyrolysis, and so on. So another difference is that single phase flow, here the continuity, all the equations are solved for each of the phases in general. But we will see that there are methods which makes a lot of approximations to reduce the computational time with certain assumptions. So we will move forward. We can see the references for more details, especially the paper by Sorel et al. They give a nice description of these equations and systematic, rigorous derivation of various simplified, simpler versions of these equations, which are extensively nowadays being used in dealing with the complex problems involving multi-phase flow with highly compressible state. So in general, these conservation equations just wrote down the physical meaning of the various terms, which again already seen in the lecture. The first term, which it represents the rate of change of a quantity, and the second term represents the net flow rate due to convection, and then on the right hand side, the first term is net flow due to diffusion, and there could be various source terms depending on the problem. This is the general form of the governing equations. You can refer to the famous book Transport Phenomena by Bird. It gives a nice description for all the conservation equations for all the quantities. So now we have a set of mathematical equations, partial differential equations. The flows or the physical problem is solved, or various calculations are done by solving these partial differential equations numerically. So for this, there are different methods. We will go through one by one. And the first one is the Eulerian-Lagrangian method. In this, some of the phases are assumed to be continuum and others discrete. Then there are a class of Eulerian methods where all the phases are taken to be a continuum. And in that, there are different classifications: volume of fluid method, homogeneous equilibrium method, and multi-fluid mode. So in the we will start with an example of Eulerian-Lagrangian framework. That is a combination of Eulerian and Lagrangian framework to solve a problem. So I will try to introduce some of the problems that we have done past along with these methods. So this problem, there is a disease called medical condition called vertigo. It's a condition where person feels as if they or the objects around them are moving when they are not. There's actually a famous movie also of the same name. And one doctor thought that this could be treated in the following way. Actually, they postulated that the reason, the cause of this disease is in our inner ear. There is a fluid, and there is something called auto leak, small particles. And sometimes these particles ideally should be in a certain place, for example, in this region, and in the canal. And sometimes these particles, they leave that place and go to some other place, disrupt and affects the working of some of the sensors or the nerve system. So the doctor postulated that if a patient is tied to a chair and this chair is given different kinds of motions and different accelerations, some of these particles can be brought back to their original position. But before doing that test, actually trying it on human beings, I wanted to do some simulations and see that this really works. So we have done this simulation using, there is a fluid in the inner air, so the fluid also moves when the person is rotated. And then there are particles, we can see in the animation, the particles also move based on the fluid flow. So we use the Eulerian framework for the fluid motion and the Lagrangian method for tracking the particles. Or another familiar example is a dust particle in a room. For example, if with dust particles from outside come through the door, the dust particles here are shown with larger scale to make them visible, but normally these particles are of the size of few microns. You can see that the particles come in, and the air goes out through the window, but due to gravity, the heavier particles settles on the floor, and as we can see, the lighter particles go out through the window. So the airflow is modeled using Eulerian framework, and the dust particles are using Lagrangian framework. So the same, this is another example of same approach. Now, how do we solve this? At this point, I would like to just mention about some of the methods that are used. How do we solve these equations? So the same equations which I had shown can be written in two ways. One is in a continuum way and continuum framework, Eulerian framework, and the Lagrangian framework. So the Lagrangian framework is also called a discrete approach because here the phase is considered, it is assumed to be made of discrete particles. So there are two methods widely used now. One is a parcel-based discrete particle method. The one is discrete element method. We will see a brief description of these methods. And in the continuum approach, there are various methods like finite volume, finite difference, finite element, that is Boltzmann, and also population balance models. So now what is happening is in the currently and in the recent past, our work also involved consolidating this. Most of these methods were available 10 15 years back, and the last few years and currently what is happening is that these methods are being consolidated and integrated with various other things to make them reliable and robust for industrial applications, and also developing more accurate methods. So we will see some of these examples. Just to revise what is the Eulerian or continuum framework. In this case, you have already seen in the previous lectures, the whole domain is divided into small control volumes, and the attention is focused on the control volume. And for each control volume, we write we look at what is there at the beginning of a time step, and then it is coming in, and then what is going out, plus what is produced and what is consumed. And that should be equal to what will be there at the end, which is of our interest. So if you translate this into terms involving rate, this is rate of change of a quantity inside a small control volume is equal to rate of what is coming in minus rate of going out, plus rate of production minus rate of consumption, and rate of absorption plus rate of absorption in the domain. This you have already seen in the first lecture various techniques how to discretize and to form the equations and to solve them and obtain the result. I will look at so I will move forward to explain how the Lagrangian or discrete approach is implemented. Look at the Lagrangian and discrete approach. I have listed some of areas of application. So these are used widely in molecular simulations or in solid particles, like modeling dust, soot particles, aerosols, burning particles, etc., or liquid droplets, gaseous bubbles, movement of large quantities. So in general, this method is used to model any object which can be distinguished from the carrier medium, like puffs, blobs of heavier, lighter fluid, etc. And in this case, the particles may interact with each other through collisions. Sorry. Look at the basic equation. I will try to explain the method for a simple problem, and then they will move to some case studies. As you know that the basic equation is determining the position, the velocity, and the acceleration of particle is the Newton's second law. So F equal to B d by dt of mv. And there are forces acting. There are four types of force: gravitational force, electrical forces, nuclear forces, and so on. You can find the details, and then you already know these details. So the carrier fluid is modeled in the Eulerian framework, and the dispersed phase, they are modeled using a Lagrangian particle method. So at each time step, the droplets or particles, they are injected or they are placed, and then their mass, size, velocity, temperature, etc. They depend on various the situations, like size distribution or their orientation. And then each particle is tracked, or a parcel of particles is tracked in the domain. Tracking means we find the changes in position, momentum, heat, and mass of the particle. And these are calculated by solving momentum, energy, and mass conservation equation for each particle. So these corresponding source terms, they are computed by considering the local properties of the fluid also. Then these source terms are added to the conservation equation for the carrier fluid. So let us look at some of the characteristics of the particles size distribution. Normally, these particles, while injecting the characteristics of the particles are to be specified in terms of particle size distribution or the distribution of their velocity, temperature, whether it is a cone, hollow cone, or they are injected straight, and so on. There are various characteristics. And the size, there could sometimes the size may be same or the size could be different, and then there are different size distributions like normal distribution or Rosen-Drumlin distribution and so on. Or injection can be continuous or it could be pulses or sine wave. And sometimes when we inject a particular certain size, and these particles may break up due to surface tension and a shear from the neighboring fluid. I'm sorry, it's a bit too slow. Yeah. So let us look at, just have an overview of these equations for the particles. The velocity of particles, velocity of a particle is obtained by the change in velocity of particle is obtained by solving the Newton's second law, and there could be different forces. One of the main important force is a drag force. This drag force depends on the relative velocity between the carrier fluid and the particle. And this shows the equation, the differential equation for the temperature variation with the time. So here the rate of change of temperature on the left hand side is equal to the convective heat transfer between the particles and the carrier fluid. And also in case of phase change, for example, if it is a droplet and if the droplet takes the latent heat of evaporation from the carrier fluid, so that term is also added in this equation. And there are various models for heat transport coefficient to calculate the heat transport coefficients. And we can write this equation for mass exchange between the phases, like evaporation or pyrolysis. You can see that all these equations have the same form. You can see that all these equations are, these are all ordinary differential equations where the left-hand side is a rate of change of momentum, energy, and mass. And the right-hand side is a set of source terms. Source terms come from various physical processes as well as interaction with the carrier fluid. So these ordinary differential equations are numerically integrated. So let us look at how these numerically integrated using a very simple example. Let us suppose there is some plane of flying, and the ball is dropped. The red color, it is dropped from some height, and it is like a particle, and it is going to fall through air, which is a fluid, continuous fluid. So the question is, what is the distance? The red ball will fall in 10 seconds. How do we find this? We know that from basic physics that we have an analytical solution for this problem. It says that the displacement is equal to half multiplied by velocity, acceleration multiplied by t square. It is an analytical equation. Suppose we didn't have that equation, how do we solve this problem? So we formulate that in terms of this Newton's laws. So first equation gives an equation for the velocity. It says dv by dt is equal to g, that is acceleration due to gravity. And the second equation, dy by dt, y is the displacement, or the height by which it falls, is equal to v. So there are two ordinary differential equations. So what we do is we convert this differential equation into difference equation. So instead of dv by dt equal to g, we write delta v by delta t equal to g. So delta v equal to g into delta t. Similarly, we convert the second equation also into a difference form. Delta y is equal to v into delta t. Now what we do is, we know at the time t equal to 0 at the beginning, y is equal to 0, and v is also equal to 0. Then we calculate, say after 10 seconds. The velocity is delta v is equal to g into delta t, that is g, let us say it is 10 meter per second square. So we get velocity equal to 100 meter per second. And then we calculate the displacement delta y is equal to 100 multiplied by 10, that is 1000 meters. So we get a result that the particle will fall by 1000 meters. But we know that this answer is not correct, because according to the analytical solution, it should be half gt square, which is half into 10 into 10 square, that is 500 meters. So why is it different, and how can it be improved? What is the reason for this? The reason is that there is nothing wrong in the calculation per se, in all these calculations. But what is happening is that we are calculating the velocity at the end of the time step, and we are using that the displacement. So this process is called a first order discretization. So we can either see which velocity should we use to update the displacement. Should we use the velocity at the beginning of the time step, or at the end of the time step, or somewhere in the middle? So your solution depends on that. So if the velocity at the beginning of the time step is used, or the current time step is used to update the position of the particle, it is called an explicit method. If you use the velocity at the end of the time step, the current time step is used to update the displacement, it is called an implicit method. Or if you use something in between, it is called a semi-implicit method. Now, instead of using the velocity at the end of the time step, suppose we use the velocity, an arithmetic average of the velocities at the beginning and the end of the time step. Then we can see that delta y, that is the displacement in 10 seconds, is equal to times the new velocity plus old velocity multiplied by time step. It is equal to 500 meters, which is the correct result. So otherwise, suppose we want to use, due to some reason, we cannot use this average, but we want to use the time, the velocity at the end or beginning of a time step, then what is required is you reduce the time step. So for example, you can do this exercise and do a simple calculation. If you use the time step 10 seconds, then you get 1000 meters per second. But if you reduce the time step you can see that the solution approaches the correct analytical solution. So what it means is that in the simulation, when you do a simulations, there, especially a transient problems, unsteady problems, the time step has a huge effect on the solution. And normally nowadays, so the inside the numerical, the softwares and the solvers, a lot of calculations are done in a somewhat intelligent way to automatically determine the appropriate time step, and most of the time the solvers use there are options to use automatic time stepping, where the software itself calculates the time step and uses that. And let us just introduce some more complexities into the same problem. So earlier we did not, we considered that the particle was falling through the air, but when it falls through the air, in the previous case, we considered only the effect of the gravity on the particle. But in addition to that, as the particle accelerates through the air also offers resistance to the movement, which is called a drag normally. So if we introduce that also, we can rewrite the equations. When there are two forces, one is helping to move the particle going down, another one opposing it. So we can rewrite, I have written down the equations. We can see these in detail in the presentation and understand. These are simple arithmetic equations. If you write down these equations and do the same exercise, we will find we can find the velocities at each of the time steps. What we will find in this particular case is that as the velocity increases, the drag force, you can see that the drag force is directly proportional to the relative velocity. So as the velocity increases, the drag force increases. Initially, the drag force is 0, but as the drag force increases, so at some velocity, the drag force will be equal to the force due to gravity. So this is called a terminal velocity. You can calculate for a typical for a human being falling through atmospheric air. You can calculate if you typical values like coefficient of drag. If you assume human body to be a cylinder, which is true at least in my case, with L by the ratio of 5 and the volume of approximately 56 liters, I arrived at from my weight of around 60 and assume that 70% of it is water. And the body density take approximately 1000 kilogram per meter cube, which is equal to that of water. And air density 1 kilogram per meter cube, the frontal area of 1 meter square. Put into these equations, we get terminal velocity of 50 meters per second. And you can check in Google what is the typical terminal velocity of, you can do a search for terminal velocity of a human being, you will find, please inform me if that value is much different from this. So the point here is that to introduce certain other terms which you might encounter in multi-phase flow analysis and in general multi-physics analysis. It's called a relaxation time. So we have seen one term, the terminal velocity, and that is also important in analyzing many of the multi-phase problems. For example, that determines the time of settling of dust particles in a room, which you might have heard in many of these articles. They are talking about settling of particles, like our new friend that we have got, the COVID-19, the virus which causes COVID-19. People talk a lot about the settling of those particles in, from the air onto the various surfaces, or in case of droplets settling and so on. So basically that behavior depends on the terminal velocity, which depends on the diameter and density of the particles and various features. So another term is the relaxation time. The relaxation time is if you introduce, suppose there is an air stream and into which we introduce, which is flowing at say 1 meter per second, and let us introduce one particle. The particle will accelerate. because the air will drag the particle to its own velocity, but it will take some time. It will not happen instantaneously. So this time is called a relaxation time. So the relaxation time is something like a response time. And every process has a relaxation, this kind of relaxation time. Momentum exchange has a relaxation time. Heat transfer has a relaxation time. Mixing has a relaxation time. And phase change has a relaxation time. So this will tell whether what kind of models to be used, what kind of approximations can be used, and so on. And also, when we do a simulation, the time step that is selected for the simulation should be based on this relaxation time. Because if you want to capture what is happening during this process, then the time step has to be less than the relaxation time. But in most of these softwares nowadays, off-the-shelf softwares, and there are methods to calculate the relaxation times to some extent, and they use these times to calculate the simulation time steps automatically. So there are certain some other characteristics and other features used in Lagrange, various other inputs required in the Lagrangian particle tracking. I have listed them here. We can go through the presentations later. So there are various models for droplet size distributions. Then there are models for spray types in case of a droplet injection, like hollow cone or solid cone. The important factor here is in interaction between particles and the walls, or the other interactions between the particles, like collisions and so on, or breakup of the particles or sprays. And one important aspect is the turbulent dispersion of the particles. There are various models for this. At this point, is it okay? Am I? What is it? Okay now? Audible and visible, or the speed is fine?
Yes, sir. Yes, sir.
Yes. Because it is very difficult to gauge the mood of the listeners here. Okay. Here, showing one of the study example just to show the result, the effects of one of the results of Eulerian Lagrangian framework. And in this problem involves flow of, you can see a pipe elbow with an elbow, and at the inlet, the steam is coming at the inlet, and or maybe hot air, I don't remember exactly. And then the liquid water is injected in the middle of the stream. So the liquid jet is continuous here, and due to shear between the neighboring air, surrounding air stream and the liquid jet, the jet breaks up and forms the particles. And the first picture shows how this breakup of the jets are modeled. And then from that, we get the size distribution of the droplets, and then that is used to track the particles further down. What you are seeing is that evaporating and the temperature variation of the particle. So you can see that from the color that properties are varying. So before going to show other examples, let me briefly explain the two different methods in Lagrangian framework itself. The first one is a parcel-based approach, in which the individual particles are not tracked. Instead, a parcel of particles are tracked. And these kind of methods are used when the number of particles are very large. For example, if you just calculate, if you look at the number density of dust particles in a room, it is of the order of 10 raised to 5, that is 1 lakh particles per centimeter. So you can see in a room there could be a very large number of particles. Even now, even with the computational power we have even now, it's very difficult to track all the particles in an individual fashion. So we use a parcel-based approach, but that has certain limitations. There could be some scenarios where the particle-particle interactions are very important, and we have to consider individual particles separately. So in that case, a method called discrete element model is used. In discrete element model, each individual particles are tracked. And also collision between particles and between the particles and the walls are individually resolved. So in this model, we need to consider various forces and movements like translation, including sliding on the walls, particles, or rotation, collision between particles and walls, or adhesion of particles or particles on the walls. So normally the inputs require a number of particles or number density, other material properties, geometry of the shape of the particles, and so on. There are two different methods. One of the main aspects, this is how the collision are modeled. There are two methods. One is called the hard sphere approach, where the particles are brought into, the collision is modeled exactly. That is, they are brought into contact in an exact manner. But it has some difficulties. One is that the time step is determined by the number of particles, the number density of particles, and the collision can only be binary because only two particles can collide at the same time. So normally there is another method called a soft sphere approach, where the particles are assumed to be more elastic, and they are as if they are connected by a spring and a dashboard. It's called a soft sphere approach. And the particles are allowed to overlap a little bit. And we'll not go into the details of how these are modeled. But there are two different approaches. We use the soft sphere approach because it's less time consuming and multiple simultaneous collisions are possible. So there are various parameters required to model particle-particle or particle-wall collision, such as in the case of a soft sphere approach, the spring constant, which is actually a numerical parameter, and the coefficient of restitution, which determines the loss of momentum during collision, and coefficient of damping and friction, and so on. So again, in this case, the position, linear or angular velocity of a particle are solved according to Newton's laws, including various forces, and also the contact forces. One difference between the parcel-based method and MA is the introduction of these contact forces. And there are normal contact forces and tangential contact forces, and there will be friction between particle and walls. I'll show one example. Here it's a very simple problem of spherical particles falling into the ground from a certain height. You can see that it falls, and then it hits. You can see that it slightly overlaps with the ground. It is zoomed out here, and that depends on the spring constant. Then it goes back. We can see that it doesn't go back to the original height. That is because we have used the coefficient of restitution less than 1, or 0.9 or 0.7, 0.5, etc. That means the collision between the particle and wall is not elastic. It loses some momentum. Or elastic collisions and inelastic collisions. So these results can be compared with analytical solutions. It has been tested and we can capture very well. See, another aspect of in DEM is that many times these parameters required to model the particle collision, such as this coefficient of restitution and other microscopic parameters, they are not measurable. So what is normally measurable is some macroscopic properties of the bulk or the bulk properties of particles. One of them is shown here, like angle of repose. You can see that here if you pour particles into a cylinder, for example, depending on the characteristics of the particles, it will form a heap kind of thing. And this angle is called angle of repose. So such macroscopic or bulk properties can be measured. And what is being done normally is that the calibration simulations are done by varying the microscopic parameters such that for a given problem, we find out the set of microscopic parameters which produce the correct or experimentally observed bulk properties. Then those microscopic parameters are used in the calculation of actual or simulation of actual problems. We have started developing this DEM and developed it mainly for the purpose of modeling bulk material handling. For example, handling of materials like coal or building materials and so on through large industrial conveyor systems or their storage and so on. You can see how the heaps are formed here, or how the particles are transferred through transfer tubes from one location to the other one. And this can be used to design the transfer tubes and see whether they are sufficient to transport these for smooth flow of these particles. So this completes that, and we will see some examples. Sorry. Briefly, we will see a problem which involves the modeling of a filter. Only a filter contains tubes of cloth. You can see that the air laden with particles, they enter through some of the holes at the bottom, and at the top they are closed. So it has to cross the cloth lining and go to the other place, and they exit. The clean air exit through the outlet at the top. So the particles are deposited on the filter. What happens is that these clothes, as you can see in your face mask, the mask cloth, they are porous surfaces. So larger particles will be collected there, or even smaller particles will be attached to that solid region, and there are small tiny holes. The air passes through the tiny holes. But as time progresses, these particles, the deposited particles, may clog the porous area, and it will increase the pressure drop across. So the pumping power will increase. So in this study, they wanted to see how the pressure drop increases as the deposition goes with time, and to see whether how frequently these are to be cleaned. So the filter tubes are modeled by surfaces. Individual filter tubes are considered, and these are modeled, these filter elements are modeled using the porosity. The porosity of a phase is less than 1. It is not completely open to the airflow, but it's only partially open. So this problem involves actually flow of air through porous media, and also along with the particles. So what happens is that the momentum equation has to be modified to include the decrease in porosity. So as the porosity decreases, that is, the air has less area to pass through, so it increases the pressure drop across the filter. So the resistance to the flow increases. So an additional sink term is added in the momentum equation, which you might have already heard about this, a Darcy. There are different models for this. One is a Darcy model, and the one is Postmeyer model to consider nonlinear effects. So some certain particle size distributions were used, and how these particle attachment to the filter is modeled is that some portion of the filter is open and some portion is not open. So using a statistical approach, it is calculated the reduction of porosity, the probability of particle getting attached to the surface, and how the porosity will be decreased. These models were built and implemented, and there are models and the calculations were done. You can see that in the simulation, as the time progresses, particles, this animation shows the particle accumulation in the filter. As time progresses, it increases. We can also estimate the pressure drop across the filter. We had some experimental data which was used for validation and further use of the model. We can find more details of this work in conference paper. You can read this for more details. And there are some tutorials also similar for the similar problems. Now, let us go to a second type of method to solve another type of multi-phase, two-phase flow problem. It's called a volume of fluid method. It is here both the phases are considered in Eulerian framework, and this method is used when there are well-defined interfaces between phases, and phases are continuous, like free surface flows or bubbles and so on. In this case, the interface is the location of the interface is calculated by solving an equation, advection equation for the volume fraction of the volume fraction of a phase. There are different methods to solve discretize this method: high resolution convective methods or geometric reconstruction methods. We can find details of the basics of this in Hurd and Eccles, 1991. And this method can be used to solve, for example, a gas bubble rising through the liquid. Here we are modeling only one half of the bubble because the problem is spherically symmetric. So we are modeling on, we are utilizing that symmetry to reduce the computational time. You can see that initially the red color is a liquid and the blue color is a bubble. The liquid has a higher density and the liquid has the gas bubble has a lower density. So due to gravity, it lifts. And while going out, it changes the shape. So this shape of the bubble that depends on various factors. Like it depends on certain non-dimensional numbers called the Bone number and Archimedes number. Bone number is a ratio of gravitational force to surface tension. The Archimedes number is the ratio of gravitational force to viscous force. So you can see that the balance between different forces like gravitation, gravity, buoyancy or surface tension and viscous force determine the shape of the flow. So here you can see that this method, these are obtained using geometric reconstruction method. This can be used to even you can model the breakup of the liquid or the bubble, or there for the transport of coalescence and so on. So you can see that these the shapes and their terminal velocities are compared with experimental results. So they predict very well. Another application of this volume of fluid method is the behavior of free surfaces, like the case of a sloshing of liquid in a tank. For example, this shows a cylindrical vessel which contains a liquid, and the blue color surface is the surface of the liquid. And this, if this vessel is suddenly accelerated, say according to the curve shown here, acceleration curve, it is accelerated for 0.5 seconds and then subjected to deceleration, then there will be sloshing of this. Because we can see that if you take a bottle, a plastic bottle, and just shake it, it is like giving accelerating and decelerating in the different directions. We can see this sloshing, the forces. So these methods are extensively used in studying the sloshing behavior of huge tanks subjected to seismic activities. In the case of an earthquake, there may be sloshing, and this sloshing may, that is, the sloshing of free surfaces may induce forces on the oscillating forces on the structure, and these oscillating forces may lead to failure of the structure. So another example is a weir flow of a fluid, liquid over a weir. You can see that here on the one side of these structures, the liquid at a higher level and is on the lower level. And if suddenly it is more liquid is pumped on the right hand side, the water level will increase here and it will start flowing to the other side. So, but after some times the water levels will steadily become steady. So you can see that the interfaces and some air is entrained by the falling liquid on the left hand side, and you can see the bubbles getting formed and so on of the different various shapes. And also these kind of methods can be used to model aerators or water purifying the place of the tanks which are used to purify water. So here the blue color region is water and records air, and air is injected with some agents, curing agents to the inlet, and they go and mix with the water, and the air escapes and goes to the ambient air above. And this is the problem which I had shown in the first slide as an example of the two-phase model to model the effectiveness of a drainage system. So we here, especially in Bangalore, we have, when it rains, there is a lot of flooding. And that flooding is mostly due to inadequacy of the drainage system to carry the water coming in. This kind of models can be used to design these kind of systems properly. So in this example, what you're seeing is a sort of garage with, you can see there's a drainage here. So in case of a leak from a tap here somewhere, and here the liquid is petrol or gas oil, it is very dangerous because of a leak. So it should be drained properly to the other places. So somewhere here in the middle, there is a leak, and what happens to whether this drainage system is capable of carrying it further. So you can see the here you see the surface. This is when it leaks, the spreading of the liquid, and it falls into the drains. And here it shows a vertical cross section of the drain showing the underground conduits. You can see the liquid falling, and after some time the pipe it gets filled, and then water level here increases. So here the simulation duration is a few minutes, but you can see the domain length is maybe 100 meters or so, very large domain. But you can see that we can capture very small features even for this large domain with kind of methods. A second type of O'Leary method we call it a homogeneous equilibrium method or a mixture model, where where we don't consider the interface. We assume that this kind of this method is suitable for problems involving well-mixed flows of multiple phases. I'll just have written down the equations used and the assumptions made in deriving these equations. We'll just skip through that to see some examples. But the important thing is that in this case, we solve a single momentum equation for all the phases, and the settling due to gravity or etc. are modeled through what is called a drift flux model using a drift velocity. This drift velocity is same as what we had seen as a terminal velocity. That is the velocity term. We have seen the definition of terminal velocity. It is the velocity, the maximum or the equilibrium relative velocity between the phases. So that is calculated and used to model the phase separation, if any. Otherwise, the equations, the conservation equations look the same, but for there is only a single momentum equation. The relative motion of the phases are modeled using the drift velocity or slip velocity or terminal velocity. So I would like to give an example of a problem which is of practical interest. And now the climate change is a big issue, and the main culprit is said to be carbon dioxide. A few years back, method was an idea was proposed, which is called a carbon capture and sequestration. Please refer to Wikipedia page of carbon capture and sequestration. People thought that to collect carbon dioxide at the sources like industries or power plants, such places, carbon dioxide is collected from the ambient air and then it is transported through pipelines, hundreds of kilometers pipeline in supercritical state. Why supercritical state is used is that in supercritical state, the viscosity of carbon dioxide is as low as that of gaseous phase or at the same order, whereas the density is comparable to that of liquid density. So the pumping power required is less. So these are transported through pipelines in supercritical state. Then these are pumped into geological storages or used to extract oil from underground or various other purposes. But the problem is that these pipelines, if it passes through residential areas, these are normally 32-inch pipes, very huge pipes. And you can see in the picture below the distance between two walls, which are used to close in case of any problem, it is about 50 kilometers. So you see that in case of a leak somewhere in this pipe, then there is a huge inventory of carbon dioxide for 50 kilometer, 32-inch pipe. You can calculate the amount of carbon dioxide. And this may get leaked into the surrounding area, and carbon dioxide is harmful, like for living organisms. So it may disperse into the air. So the objective of this project was to calculate the spread of carbon dioxide into the surroundings in case of an accidental leak. Actually, we had to provide a customized tool to do these calculations. So in modeling this, the difficulty is that there is transition from the carbon dioxide inside the pipeline is in supercritical state. So first, during a leak, in case of a hole in the pipe, the outside pressure and pressure is 1 bar and the temperature is say like 30 degrees centigrade. So there will be transition from supercritical to first to two-phase liquid, and then it will evaporate. And there could also be due to flashing, due to decrease in pressure, and then there could be formation of dry ice once it comes outside. So you can see that from photographs, some of the photographs in case of such a leak. So another difficulty is this steep variation of properties in the supercritical state near the pseudo-critical point. So in the phase diagram, if you look at, there is a point called a pseudo-critical point, where the properties, you can see on the right-hand side, so the properties like specific heat changes suddenly with the temperature. So this poses another difficulty. Another difficulty is we have seen that the pipe length, inventory length is in hundreds of kilometers, or at least 50 kilometers, whereas the leak diameter could be as small as 1 millimeter. But the total calculation domain is many kilometers. Both inside the pipe as well as outside the domain of calculation is many kilometers. So we have to model a multi-phase flow starting from the supercritical state inside the pipe, and then the expansion through the inlet state of fluid is supercritical, then exit state of fluid is at subcritical pressure, which could be a mixture of liquid and gas. So we have to we use the homogeneous equilibrium model to model this problem and get the leak rate in case of such a leak. Okay, and there were some experiments conducted to validate the code, and this model could predict both the pressure variation as well as the flow rate reasonably well. And then this after this model was built in, and the customized version of software was made, and it is used by client to model various scenarios involving various wind conditions and so on. This picture shows pictures of some of the results of carbon dioxide dispersion in the atmosphere in case of a leak from the high pressure tanks and pipe. So this is the dispersion at different times for different wind velocities. And this there are hundreds of scenarios to cover for all the probable conditions. Normally, when such installations are done, it could be carbon pipes carrying carbon dioxide, or pipe carrying. Nowadays, we are all seeing about liquefied natural gas pipelines throughout the country. So these kind of models can be used to evaluate the risk and the consequences from such accidents. And can see that the problems involving multiple scales and the length scales and time scales can also be handled with appropriate parameters. So you can find more details. We have published a paper. You can find more details in this paper, published, presented in the conference. Numerical modeling of supercritical carbon dioxide leaks and its subsequent dispersion in the ambient air. So another problem which is used in concrete forming. Concrete forming is a process of making concrete which can be painted. This is done by concrete is normally a non-Newtonian fluid, slurry kind of thing. You pour hydrogen peroxide into that, and hydrogen peroxide gas then dissociates, and the gas bubbles of oxygen are formed, which is actually an exothermic chemical reaction. And these bubbles will make these concrete like foam, which can be used to paint using brushes or various means. So this is called a concrete forming. So here there are two phases. One is concrete, and then there is bubbles of oxygen, which is in the gaseous phase. So you can say that it is a gaseous bubble flow in a non-Newtonian fluid, along with chemical reactions and heat release. I'll just show some more the results. So in this case, we have used a homogeneous equilibrium model. So what you see is that in the beginning, this is a cylindrical vessel, and in the beginning, the concrete, the red patch shows the red color region is the cement, and onto that hydrogen peroxide is poured. Then oxygen bubbles are formed, and you can see that actually what is plotted is a volume fraction of the liquid. So you can see that the liquid actually goes up as a form. So coming to the next model, in previous two methods, that is in volume of fluid and homogeneous equilibrium model, we are solving only a single momentum equation, and the relative motion of the phases are modeled through what is called a drift flux model. And there is a most general method is to solve all the momentum equations and all the governing equations separately for all the different phases. You can find more details about this model and how the implementations and so on, if somebody is interested in developing such models, in a paper by Darvish, Mukalat, and Shekhar. And it describes in detail how these methods can be used for flows of all the speeds. So I'll just show one example where these methods were used. This method was used to model flow in a heat exchanger. In this case, there is a heat exchanger which is horizontal, and at the inlet on the right hand side, a mixture of liquid and vapor comes in, homogeneous mixture of liquid and vapor comes in. So what is plotted is the volume fraction of the liquid. So you can see that as the flow progresses, the gravity is acting in the downward direction. You can see that liquid gets settled, there's phase separation, the liquid gets settled, and some liquid is trapped in this place, and the vapor on top goes up through the to the channels. So first picture shows the volume fraction, second one shows the mass fraction. I can clearly see the settling of the liquid here. And this, you can see that this simulated result similar to the experiment. These were compared with flow visualization of one of the scenarios and found to be satisfactory. And finally, I would like to introduce another type of method, class of method called a population balance based multi-fluid model. I will introduce this method, the framework of a practical problem. This is a problem in steam turbines, the condensation of steam in a steam turbine. So you know that in a steam turbine, there are blades, and the pure steam comes to the rotor, and as they pass between either the rotor blade or stator blade, the steam expands and accelerating, and which produces forces and of course the rotation of the turbine blades. So now during this process, as the steam loses its energy, there could be nucleation. and that is for condensation. And once these nuclei are formed, there could be growth of this nuclei and formation of the droplets. And this formation of the droplets is accompanied by energy release, which may lead to shocks. So you can see that here between the blades, small droplets may be formed, and they may grow. These fine droplets may grow, and some of them will become coarse, and some of them will impinge the turbine blades and form a small film on the turbine blade. And this film will flow along the blade, and a part of this film may get separated again from the film and forming coarse droplets, which may go to the next stage. So in general, these droplets or water formation or condensation of steam inside these inside the turbine cause a lot of problems, like it will affect the efficiency of the turbine or even mechanical strength. It may weaken the blades. So objective of this model is to check in the design normally what is certain passages called water trapping regions are designed to capture these condensed water and to remove them from the system. So this project involved modeling of this process, that is process of nucleation and its growth and wall filling formation, and then further separation and breakup and so on. One important thing is that the nucleation takes place in a non-equilibrium manner. That means so normally we know that there is a saturation curve, that is for a given pressure, it condenses at certain temperature, which we call a saturation curve. But normally, it doesn't happen like that. Nucleation takes place when when the steam gets cooled. The nucleation takes place at much lower temperature in a subcooled region. It is called a Wilson region. So in this case, the non-equilibrium behavior has to be considered. So in this case, you can see that the steam is like a gas flow. And the droplets are in liquid form, so that it is treated as another phase. But here you see that there could be large variation of the particle sizes. The particle size may vary from a few nanometer to few microns. So there is a method called multi-fluid method in population balance based. You can find the details in the reference mentioned below by Laura. Here, what is done is, so there is a distribution. We don't solve for each. The particles are also solved in an Eulerian framework. So we make bins or classes of particles, and the scalar equation is solved for each particle size or each band of particle size. So you can see that the distribution, normal distribution, as shown in the picture here, the normal distribution of particles, it is divided into packets. And for each packet, a conservation equation is solved. For each packet, we can solve mass conservation equation and momentum conservation equation, and so on. There is another, so if there are 10 packets, then we need to solve for 10 additional equations for mass conservation. And as there is condensation, the droplets in the lower diameter packet, they will move to the larger diameter packet. So there is a source or sink time or interaction between the packets of the droplets. So this is called multi-fluid method. There is another way of treating the same problem. Instead of solving different equations for each particle size, we can solve for moments. It is called the quadrature method of moments. I'll not go into the details of that. You can see this in this if somebody is interested, we can discuss individually. So here, normally, what we assume that in a one moment method, each particle group, it has the same properties, a single value. There is no variation across that size bin, but that is not strictly true, because the particles don't exist in discrete sizes. There is a continuous distribution of the size. So this one moment method is what is shown here is the one moment method, that droplet, for example, one density for surface area, it is constant in each bin. But that is not true. We can see that the curve, there is a variation, continuous smooth variation. So in the two-moment method, variation is also considered. For the same packet, the variation of the different quantities, it could be of the size of the area, surface area, etc. They are considered, because this is like a second order method numerically. And then additional models for nucleation, equations for nucleation and growth rate are included. And it is validated for test cases and solved for a problem involving converting diverging nozzle, which is called, it is a very popularly used problem for validation or benchmarking the numerical methods. This involves converging, diverging nozzle with the steam coming at the inlet and pressure drops, and there is condensation, nucleation, and condensation in the domain. So if you look at the result, what is plotted here is the pressure variation. So as the steam passes through the nozzle, the pressure drops, and then when there is a sudden condensation, you can see that there is a shock due to release of heat. And I have mentioned about the non-equilibrium flow, that is a departure from a saturation curve for condensation. So in the picture on the right-hand side, that the green curve shows the result obtained using equilibrium model, that assuming that the steam and the liquid are in equilibrium, and you can see that it doesn't capture all the features properly. This model, it considers nucleation and condensation is modeled as a droplet streams, again in Eulerian framework, but there is also impingement of droplets on the wall, so which leads to a dynamic wall films, that is films which are changing in thickness and position with the time, and there could be detachment of the wall films from the surfaces. So in this case, we had to use different methods for different flow regimes. In this case, we used a Lagrangian or the population balance based methods for Eulerian for droplets, Eulerian 2D model for the wall film, which is treated as continuous, and again Eulerian or PBM model for the detached liquids. Complete this by showing some examples of wall film calculation. There is a test problem, a benchmark problem given by Frederick et al. On separation of wall film. So what happens is when film, liquid film flows over a surface, we can see that there is a liquid film, and over that there is a gas flow. At the corner, a part of the liquid goes straight, and some part of it is attached, remains attached to this. So after detachment, there is a shear layer. These film may get disintegrated or broken up to form droplets. So we can use the Eulerian framework, the 2D wall film model in this region. And then here, it's also used for this region where the film remains attached to the wall. And here, once the droplets are formed, they are modeled. They can be modeled using the population balance model or Lagrangian model, provided these two methods are coupled properly. So here I show some results here. So here, initially there is a film here. The film is not shown here. In this part, it is too small. Then you can see as time progresses, the film gets detached. These are actually a droplet stream which is obtained using the population balance model. So in the third picture here at time t equal to 0.21 second, shown the zoomed in view here, you can see that the droplets or the detached stream goes here, and you can see another portion which remains attached here. And finally, there is a recirculation of this. So similarly, similar test case is available for impingement of spray onto the wall, and then subsequent formation of the film and its detachment from the surface. So here you can see that the droplets are injected here, and they impact the walls, forming a film, and then whether a particle stream will impact the surface, it depends on the size of the particle. So what is shown here is the particle streams, the contours of particle streams with the different diameters. The top one is with the lowest diameter, and the bottom one with the largest diameter. So as you can see, and there is an airflow along with this. So you can see that for a smallest particle, the terminal velocity is less, and it gets carried away by the air. It doesn't reach the bottom surface during the stay in this region. As the particle size increases, the terminal velocity increases, and it comes more and more near to the surface. And for the last particles, they impact the surface, and coarser particles impact the surface and forms wall film. And that film progress. And on the right side, the calculated liquid film height is compared with the experimental data from the reference. So I'll summarize my presentation with this. So multi-phase flows exhibit various physical processes with a wide range of length and time scales. But with the current development, the large-scale problems, even sizes involved, and domain sizes involved, extending to many kilometers, a few meters, even with minute scales, can be modeled, and the newer methods with better resolutions are being implemented, with like a discrete element method are being implemented with increasing computational power. And for more and more complex problems, it is essential to combine different methods for the same problem. And in many cases, the multi-phase problem, one of the phase may actually alter the geometry, as we have seen in the filter, or in sedimentation problems. They may change the geometry characteristics, and it will affect the other fluids. So with this, I stop my presentations, and we will see some more examples related to nuclear industry tomorrow, with a little bit complex problems. Some examples involving condensation and flow through porous media, and such things in the session tomorrow on nuclear industry applications. So, thank you for your attention, and I'm sorry if it was not as clear. please feel free to communicate to me or any more clarifications for the discussions.
So there are few questions in the chat box. I think you can see that.
Okay. Dr. G. Sendil Kumar, what are the forces accounting for source term and a separate term in Navier Stokes equations? I suppose your question is with respect to multi-phase flows or in general Navier Stokes equation. Dr. G. Sendil Kumar. Okay, in general, there is a source term to take into account gravity, there is buoyancy, okay? And then if you there could be some other forces due to external things like due to magnetic field, there could be some forces which has to be added as a source term for the momentum equation. We will have a different separate session on that day after tomorrow. Then otherwise, when we come to the multi-phase flow, if there are two phases, for example, then there are different types of forces acting on one of the phases. Let us take suppose the particles moving through a stream. There is the force due to drag, that force on the it has to be added as a source term to the momentum equation, and the same whatever momentum transferred from the carrier fluid to the particle, it has to be subtracted from the carrier fluid. That is, suppose we have a stream of air which is moving at 1 meter per second, and into that, if we put some particles which are at zero velocity, then this particle will gather momentum. Momentum will be transferred from the air to the particle. And this is a momentum transfer from the fluid to the particle. So this is added as a surface force or source term to the particle momentum equation. At the same time, the same amount of force should be, or momentum should be subtracted from the momentum of the air. Then only we will get the correct flow field. So that goes as a negative source term for the Navier-Stokes equation for the carrier fluid. Now, then there could be pressure forces. Then there is something called a thermophoresis. Thermophoresis is a movement of a particle, movement of a discrete particle due to the temperature gradient. For example, if we consider one particle in a thermal boundary layer, you look at the particle in a thermal boundary layer, there is temperature variation. So this particle will experience higher temperature on one side and lower temperature on the other side. And as we know, the temperature is a measure of the thermal velocity, kinetic energy of air molecules. So on the side where the temperature is higher, this air will be exerting more momentum. And on the other side, it will be less. So this particle will move in the direction of decreasing temperature. So that is why you see in the old lamps, kerosene lamps with a glass cover, you see the soot particles getting deposited on the cooler side as it goes up. It is due to the plate, the surface, the glass surface is cooler than the incoming stream. So the soot particle from the incoming stream goes to the walls and deposit. This is called thermophoresis. Then there is something called electrophoresis, which we will see in this session after tomorrow. So these are then there are certain additional terms added to take into account this virtual mass force, Sofman force, due to velocity gradients and so on.
So what about that centrifugal force? That centrifugal force, Coriolis component, and EMF. In some cases,
Yes.
they may be considered as a separate term. If I am right.
Yes, yes. For centrifugal force, if we solve the equations, if we rewrite the equations in terms of, see, we can write the equations in Cartesian coordinate, or we can write the equations in a rotating frame of reference. So when we write the equations in terms of rotating frame of references, then these centrifugal forces are to be forces are to be added separately. Otherwise, if you are solving it in a Cartesian coordinate system, these will come automatically in this. And EMF, I mean, you mean electromotive force, correct?
Yes, sir. Yes.
Okay. Yeah, we will see this in session day after tomorrow. Yes, this is what I have mentioned about these problems involving MHD, magnetohydrodynamics. That, for example, the flow of a conducting liquid under the influence of a magnetic field, there will be, when there is a liquid flow with ions in that, charged particles in that, it means it is like a current. Then, if there is a magnetic field around it, it is like current flowing through a magnetic field. It will induce a force called a Lorentz force. So that is added as a source term into the momentum equation. So yes, they are also added in the problems involving magnetohydrodynamics. You are right. Clear?
Yes, sir. Yes, sir. Sir, sir
Okay.
one more question. Sorry to disturb. For some hydraulic structures, for example, open channel flow passages, we are conducting the experiment under laminar flow conditions. But
Okay.
while doing the experiments on the downstream side, for example, it leads to the turbulent flow conditions. That is entrainment of some gas, entrainment of air, for example, in water. Okay.
Yes.
But
Yes.
initially, I started the experiment with the laminar flow conditions only on the upstream side. For example, the flow over the spillway vias, if I'm right. On the downstream time, when the water falls over the spillway via, there will be the large entrainment of air. So I need to calculate the volume fraction of air, the depth of penetration, and all those things using any techniques like image processing or what may be that. So now it is a turbulent in nature. So how I can handle this in the software effectively?
I have shown you an example of a wire flow. It is
Yes,
actually
sir, yes.
similar to what you have seen.
Yes, sir.
So
Yes, sir. Yes, sir.
you can use, if you want to model this kind of problems, you can use a volume of fluid method with a geometric reconstruction.
Yes, sir. Yes, sir.
Yes, you have seen the capturing of entrainment bubbles in that.
Yes, sir. Thank you, sir. Thank you, sir.
Okay, we'll go to the next question. Sorry, I'm new to this process, so I'm finding it a bit.
Sir, shall I read the question, sir?
Yeah, okay. Mr. Hari Guru TM.
Yeah.
May I know what is the difference between FVM and FEM, finite volume method versus finite element method? So in finite volume method, we discretize the whole domain into control volumes. And if you look at the fluid flow equations, which you can read from Berg et al., these conservation equations are modeled in terms of flow, that is flow rates through the phases of that control volume. And I have written in one of the slides, you can go through those slides. I will be sharing this presentation with you, so you can go through the slide. I have written in terms of in the common terms, what is meant by the different terms in the equation. So in finite volume method, the properties are assumed to be uniform in one of the in this element. Can you see my screen?
Yes, sir.
Presentation. Okay. So in finite volume method, we write this equation for each of these control volumes. control volume means a small volume. You might have created a mesh yesterday. So what I mean by control volume is one of the elements, one of the volumes. And the fluxes through different phases are calculated and the equations are reformulated, and we obtain the values of the different properties inside that element. Now, in the case of finite element method, we look at the nodes of the elements, and the certain the variation of properties are fitted in that, and different method the values are obtained at the nodal values. So you can say that finite volume method is a flux-based method or flow rate flux-based method, whereas finite element is a kind of nodal-based method. Actually, in the next session, I am not an expert in finite element method. In the next session, my colleague, Dr. Suresh, who is developing our finite element software, finite element module, will be participating. The next session is on fluid structure interaction. So you can get more details about finite element method from that. But in general, finite volume method is a flux or flow rate based method. That is why it is suitable for any process, either fluid flow or even electromagnetics, where the field flow of various quantities are concerned. Okay. What are all the software would be suitable for FEM and FEM? There are many softwares including Fluidine, and inside Fluidine MP we have both FEM and FEM. We use FEM for fluid flow problems and FEM for structural analysis. And there is a message from Arun Murthy, I think it is answering the question. Yeah. I think here, Mr. Arun Murthy, I don't know whether Arun Murthy has.
Yes, sir. He has answered a few questions in the chat.
Few questions. Okay, then is it possible to get the questions which are not answered?
Yeah,
because we are short of time.
Yes, sir. I think almost every question Arun sir has answered.
Okay, thank you. Thank you, Arun, on this. Yeah. So then please
Any more questions
inform me if there
Monica,
is
sir?
something is not answered, please.
Yeah, I'm checking, sir.
Yeah. Sure.
No,
We will
sir.
share the content.
Yes.
I will make some because some of the things I cannot share. Okay, but some of the case studies I take out. I will make a PDF and share it with you.
Sure, sir. I think no more questions, sir. Everything is answered.
Okay. Okay. Then we will be actually we will be saving this chat the transcript. Correct?
Yes, sir.
Okay.
Okay, sir. Thank you, Dr. Anil Kumar, sir, for a very precise and relevant presentation. I think everyone has got very good knowledge about what you have spoken right now. Thank you for all this information. Now we will take a short break and we will resume back at 11:15. Thank you very much, sir.
Okay. Thank you.
Thank you, sir. Yes.